Hi, I'm Julian and I'm a senior machine learning engineer at DeepSet. And in this talk, I will present to you how to build a question answering application with the open source framework Haystack in just under 30 minutes. So let's get started. I would like to start with the basic motivation, why you might want to build a question answering application. And the reason is that there are many search tasks in our daily life. And searching through a large amount of documents, for example, here these clinical practice guidelines, takes a lot of time. So imagine you have a question in mind and you search the answer somewhere in these documents. Basically, you would need to read through all of them to find the answer. Maybe you just scanned the headlines or the abstracts of the papers and now already know which one is the relevant file for you. But still, even searching the answer in this one single document is very slow. So this is where question answering comes into play, because question answering can exactly do this for you. It can, given a large corpus of documents and given your query, find the most relevant document and then extract the answer to your question or multiple answers to your question from that document. So here's an example. We have this document and the question is, how many people are affected by cancer-related fatigue? And imagine we have found this document now through question answering application. What the next step is, what the application does for you, it will extract the answer to your question and highlight it in the given context. So we can read here the answer now, but we can also see what is the sentence before that in the text, or what is the sentence after that. So we can better understand the context of that answer. And this is called extractive question answering, because it really extracts the answer from the text and does not generate a new sentence or a new text. And in contrast to larger language models like ChatGPT, for example, that you heard of, this model does not hallucinate. So it can never come up with an answer that is not somewhere in the text. And thereby you can rely on that any answer that this model finds is also somewhere there in this text, in this document. And you can look at the context and see whether it answers your question even in that context. Another advantage of extractive QA is that the models that you need for that are relatively small. So you can run these models and these question answering applications even on your local machine. And this is what I actually did for this talk. So we can have a look at the demo right now. So this is the demo running here right now. And what you see is a very simple search interface. So nothing super fancy. But the cool thing is you can enter here your text question. And I have indexed about 100 files. The 100 files are just practical clinical guidelines. So here's the list of files. To give you an example, this is one of the files, right? So it's just PDFs. In fact, a number of pages in this PDF, so too much to actually scroll through. And this data is now all indexed in this demo. So the model has access to all these documents. And when I click run, I try to answer this question. And what the model does, it finds the most relevant documents to that question, and then tries to find the answer in these documents and outputs them here, sorted by the relevance to the question. So for example, here, the highlighted answer is that the diminished energy and increased need to rest is one of the symptoms of cancer-related fatigue. And I can see that the model is relatively confident that this is a relevant answer to our question. And I can also see that this comes from this document. In this case, because of the file name, it makes sense that this is a relevant document. But it might not always be the case. So the model uses much more information, obviously, than just the file name to find the relevant documents. I can also try some other questions. So what are the treatments for this kind of cancer, for example? And we can see that there's a special type of chemotherapy or chemoradiotherapy. I can try to answer this question about pain for cancer patients and how to treat that. What I can also do here is I can show you how to upload files. So if you want to build that demo your own, there's not much you need to do. And in fact, when you have it running, you can also add files from your disk. For example, I can add this file, and then what we see here is that it was indexed. And indexing means the model, our language model, the model used for the retrieval of documents, processed that document and calculated an embedding for this document. So this document now is actually stored in a special kind of database that we can query and that we can use with these full text questions. So it's not a keyword-based search, but I can really type in fully fledged questions as a full sentence. This demo is, as I said, running on my local machine. So when you try this out, there's no risk involved when it comes to the data set, right? Because all the data, all the documents remain on your local machine. What you can also try here is you can try out these different parameters. So as you see here, we get 3 answers to the question right now. And I can also change that parameter and say, maybe I want only 2, or maybe I want 4. And if I then pick, let's say, another question, I can run it. And then I get 4 answers now. Right now, the model is retrieving the top 3 most relevant documents from our 100 files in the database to answer that question. So it actually only looks in these top 3 documents then for an answer. And this is the second threshold parameter here. So I could also say, let's search in more documents. Let's search maybe in 4. In this case, the answer won't change because the top document was also the most relevant one here, which is the right one for these answers. There's also an option to show a debug info, and this debug info is for people working with the REST API of this demo. So you can see here the answer of a REST API. For example, you can see the offset in the document text that is used for highlighting the answer, right? So this is the offset in the document. And if you build your own UI around that, you can build it based on this REST API JSON response. There's another mode that you can use in here, which is the evaluation mode. So when you show this to users and they try out this prototype, they can leave their feedback here with a thumbs up, thumbs down, based on whether this answer is really the one they were looking for, given that question, or also if they are not sure, right? So part of it is correct, for example, this passage, this document, but the answer is still wrong. So the model didn't really solve the task completely, but it was still helpful because you have a relevant context at hand. Okay, so much for now about the demo. Let's get back to the presentation. So now you wonder, how can I build this demo, right? How can I build the demo with my own data? And the answer is you only need 3 Docker images. So these 3 Docker images, they are one image for the data. In this example here, it's an Elasticsearch instance that keeps the data in the document store, as we say. The second one is Haystack as one Docker image. So this is the open source NLP framework I already mentioned. And it is the one where the actual question answering happens. So the retrieval of the documents from the document store, for example, the processing of the query, and also the extraction of the answer. And the third Docker image that we have here is Streamlit. So this is for the UI. And in fact, you can use these 3 Docker images to run this demo that I just had with only a few commands that I will show you in a second. But you can also run only parts of the demo. So for example, you can easily swap out the Streamlit UI with a different UI that you want. Or you could swap out the Elasticsearch image with a different one. It could be another Elasticsearch instance, but with other data already indexed. But it could also be a different kind of document store. So another vector optimized database, for example. And how do you get these 3 Docker images? So first of all, if you want to run this demo, you need Docker installed. And I'm referring here to the Docker installation guidelines. The second step is you need to clone a public GitHub repository. So you download this on your machine, and it's a Haystack demos repository. And when you're in this folder on your machine, the only thing you need to do is to run this docker compose up command. And this will build the Docker containers from the images, from Docker files. and we'll also start these containers. So you will have in Docker then 3 containers running. One for the data, Elasticsearch in this case, one for Haystack, NLP, so the API of Haystack, and the third one is the UI. So I think how Elasticsearch works as a database and how a Streamlit UI works, we can with the Streamlit UI we saw in the presentation, and Elasticsearch basically is just the data container. But I didn't say so much about Haystack yet, so this is what I want to explain to you in the next few slides. So Haystack is an open source NLP framework, and it's built for many different NLP tasks. So it can be used for many different semantic search tasks. For example, it could be used for the question answering that we saw today here, but it could also be used for summarization or just document retrieval, but with semantic search. So with actual sentences as input question, instead of just keywords, and then returning documents. And also it's well integrated with the Hugging Face Model Hub. So this is the place where you can get these different language models specialized for the healthcare domain, tailored to that particular domain, or maybe even to subdomains, to oncology, for example. And the framework does not only focus on the actual querying part that I've shown you so far, but it also supports you when you want to index your data and want to add data. So I showed you that you can upload files. That means load files to my local Elasticsearch instance. So not upload to the cloud or to the web, but to my local Elasticsearch data container. And before that can happen, I actually need to convert these PDFs to text data. And this is what automatically happens then in Haystack. So you see in this graphic here that there's an indexing pipeline that is used when you add a file, and you have a search pipeline that is executed when you query the application. And the features of Haystack are that you can build these pipelines, these two, and in particular the search pipeline, with different nodes, with different components. And this allows to cover many different NLP tasks. So for example, there's a reader node, and this component extracts answers from a given short document. Then there's a retriever that can, from a large amount of documents, retrieve the top relevant ones, given your question. There's also a summarizer that takes long documents and creates a summary and makes them shorter. A ranker that can re-rank documents in a list based on some ranking criteria. You have classifiers that you can use to classify documents, but there are also even nodes for named entity recognition. And there are query classifiers. For example, if you want to, before you actually run a query, decide what kind of query it is. Then for the indexing pipeline, I mentioned there are different data connectors. So first of all, different file converters that you can use to input text documents or PDFs or Word documents or Markdown files, whatever. There are even nodes for web crawlers or web scrapers, where you can put a URL of the website and then scrape a few pages from that website to make them searchable in your pipeline and add them to your document store. And the pre-processing of these files is also handled then by Haystack in this indexing pipeline, where you can specify, for example, how to clean up that text that you got from the files, or how to split it in shorter paragraphs that are better to search. And the third component are the document stores. I mentioned Elasticsearch for this demo running here right now, but there are many different document stores supported in Haystack. For example, OpenSearch, SQL document stores, but also Phase, Milvus, Weaviate, Pinecone, Quadrant, and potentially many more, because it's easy to add a component, even like a custom component, to the existing components we already have. The pipeline I showed you in the demo is the following. So we have a document store where we have a clinical practice guidelines about oncology as PDF files indexed. This means for every text there, we also have a vector embedding calculated. And the second part is the question answering pipeline. And in this simple example, it takes the query as input, retrieves the top relevant documents, tries to extract the answer from each of these top relevant documents, and then returns the answer candidates, so all the answers it found in a sorted order to the user. There are also other pipelines you can imagine, and you could easily change the demo if you want to try out a different search use case. So for example, maybe you have in mind summarization. There you can have a query again as input. The retriever will also again retrieve the most relevant documents, but then instead of trying to extract an answer, we could use a summarizer node. And this summarizer would simply load a model from the Hugging Face Model Hub, for example, or a model you have already available locally. And this model would generate a summary of the long document to provide a shorter summary to the user. And then you could return that summary again to the user, maybe also store it as metadata of the indexed file. And the third pipeline we see here is a hybrid retrieval pipeline, where again we have a query as input, but before we use the retriever, we actually classify it. So this is the query classifier. And in this case, the distinction could be whether the question is actually a full text question, or if it's just keywords, because some users, they are not already familiar with these new search interfaces, and they might still be using just keywords and not these full text questions I showed you. And in this case here, we can then use different retrievers for the kinds of query we received. For a full text sentence, we can use dense retrievers, which means retrievers working on vector embeddings. They will calculate an embedding of the full text question, and they already calculated embeddings for all the indexed files, so they can very quickly compare which of the files is most similar to the question. And the sparse retrievers, in contrast, they don't need the embeddings because they just get the keywords in, and they will, as usual with older search systems, just search for the most relevant documents based on the keywords. And in the end, you can join the results and you get back a list of documents that you can again rank, so that you have a list of documents that were relevant because of the matching keywords or based on the matching embedding of the close neighborhood of the query and the retrieved document in the embedding space. These Haystack pipelines you can build in code, in Python code, so you can write them line by line. Another way that doesn't need code is pipelines in YAML format. So here you can see actually the YAML file that I used in our demo for specifying this particular search pipeline. So you see we have an Elasticsearch document store, as I mentioned, and this one is running locally. So I have this parameter localhost so that it can connect to my Elasticsearch service running locally. I also, for the embedding retriever, specified a model from the model hub, so the sentence transformers model here. And I specified that I want to return the top 10 documents from the retriever. I have a reader model here, which is specialized for the biomedical domain. And I specified also that I want to, with an answer, return 700 characters of context around the answer. And you can see I have the PDF converter because we added files that were PDFs, not just text files. So I need a converter that processes PDFs and makes text. And then when I have all these components specified and described, I can combine them in a pipeline. So I can define in which order should they actually run in my pipeline. And here we see the query pipeline with the query first, then retriever and reader. So very small pipeline, you could say. And we have the indexing pipeline, which starts with the file, then the PDF converter, then a preprocessor. Remember that maybe cleans the text file or splits it into smaller chunks. We have a retriever because for every file we add, for every document we add, we need to calculate an embedding. And finally, we store the text and the embedding in our document store. Something that I also want to show you here in the session is the Haystack API. because it's super cool when you build these demos to not only try things out in this UI that we have here, but you can even have a look at the REST API calls that are sent and processed then by Haystack. So let's look into that. So this is the documentation. We can also make it a bit larger. And this is the API reference of Haystack. So we can see here the different API calls that we can make. For example, we can in search make a query, which is a post request. And what we see here is the post request, also, for example, as Python code. And if you want, you can even try it out right now here, because we can specify the parameters when we send that post request. For example, the string, the query is required. That's the only required parameter of the query. So I put here our question: what are the symptoms of cancer-related fatigue? And then all I need to do is click try it. And what happens now is that the post request is actually sent, and it's sent to this address. So to localhost at the port 8000. And this is the port where I have my demo running right now, where I have the Haystack API container listening to any requests. And if you have this running, just as when you try out the demo and run it with Docker Compose up, you will also be able to do that. So you can try out the API without the need for the UI, for example, for the graphical user interface. And you can look at the response that you get back. You can even try out setting other parameters. You can change the parameter here. So it's an easy way to try out the REST API besides looking in the UI. And with that, the question is, what's next? So now that you have your demo running, that you tried it out, that you maybe even played around with the REST API, what would be the next steps? So I'd recommend to try out different pipelines, because once you have this running demo, it's easy to use a different YAML file. We even have specified like templates or predefined pipelines that you can try out. But you can also make easily changes to that pipeline. You can try out, for example, this hybrid retriever that I mentioned, with a retriever that is useful for keyword questions and a retriever that is useful for full text sentences. I showed you that there's this user feedback option with thumbs up, thumbs down. So you can collect this user feedback when you run this demo and show it to users. And you can even use this user feedback to create a small data set that you can later on, for example, use for training. You can also annotate a real evaluation data set. And that way you would, there you would probably not rely just on user feedback, because there it depends on what kind of queries users execute. But you would go create a random sample of a larger corpus, ask annotators to find the actual answer to a question, and in that case by hand, just to evaluate later on how good is your question answering pipeline. You can also tune the parameters in the YAML file and see then, based on your evaluation data, which parameters work best in your scenario. If you have even more evaluation data, you could decide to split this data set into a training, validation, and test set, and use the training data set to fine-tune your language model. So not use just a biomedical bird model, for example, but a fine-tuned version of that, really specialized on your particular domain, your kind of questions, your kind of documents that you usually search through, the vocabulary used in them, and so on. When you go towards production, also model size plays an important role, because this influences the computational resources you need. And reducing the model size is also possible in Haystack. It's called model distillation, that process, where you have a larger model that is solving a task, and now you want to shrink its size in the terms of memory it needs, but also runtime it requires for every query. You can calibrate the confidence scores that the model returns. So these are, for example, these relevance scores we saw in the demo, and these depend on the domain, specific data sets. So if you really need these confidence scores to decide whether you can rely on an answer or not, it makes sense to calibrate them further. And one more thing I would recommend to try is a special kind of pipeline again. And this is a pipeline that works on tables. So you can also try question answering on tabular data. For example, in the PDFs, there's oftentimes also a table, sometimes with numbers, but also with text. And we have pipelines that can pre-process these tables. And they can also be indexed in a data set. And then you can query your question answering application. And if the answer is in one of the tables, you will also get the cell of the table where the answer is together with the context around it. And of course, there's no limit, so you can combine this tabular QA with the QA I showed you today, and you can build the pipeline that you need for your use case. And with that, I wish you much fun in trying out these pipelines. So check out this GitHub repository. Again, Haystack is open source. Try out running the demo. Just download the Docker images, run Docker Compose up. You can upload your own files. Again, it's only loading the files in your local machine. So the data will stay with you. It will not be sent somewhere else. And then you can try out different pipelines and see what question answering application is useful in your use case. Thank you.